Kenapa ada dua Maisarah kan? Masuk admin. Okay. Alright, so the password for today will be Muhammad sallallahu alaihi wasallam. It's Maludur Rasul. Right. So you can go to the link, put the password today. Muhammad sallallahu alaihi wasallam. Okay. So let's continue from before. Let's continue. Do you remember where we left last time?
Balance band and conduction band.
Balance band, conduction band. Do you have any question regarding last time? Anybody? No? Yes, no? Answer.
No.
Okay, so what should we do next? What else did I ask you to find out? Fadli?
But then didn't ask us to find anything because you said we will have class today.
Tak dengar.
But then didn't ask us to find anything because we will have
Sebelum
class
ni,
today.
I think semua list saya yang sebelum ni pun tak habis lagi.
Oh, Fermi level. I
Okay,
guess.
good. What is Fermi level, Fadli?
Is referred to the highest occupied molecular orbital at absolute zero. It will determine the probability of electron occupancy at different energy level.
Do you understand, Faris? Faris, can you hear me? Ada dua orang Faris. Okay, ni Faris. Seorang, so how do I differentiate between both of you?
Is it me, madam?
Ah?
Is it Faris me or the
Betul
one?
lah, macam mana saya nak differentiate, saya nak panggil apa?
You can call me Faris Apandi.
Yang tu Faris saja.
You can call me Faris Azim.
Panggil Pak Azim je tak boleh?
Okay.
Tapi can you change your name kat Zoom tu nanti jadi Azim ke Faris Azim ke, you know, dan apa nama ni, it's easier.
Okay, Prof.
Hey, Azim. So Azim, tell, do you understand what Fadli was saying?
I couldn't hear him clearly. I'm sorry.
Okay, ask him to repeat.
Fermi level determine the probability of electron occupancy at different energy levels.
Okay.
Do you understand?
Yep.
Okay, tell me what you understand.
Based on my understanding, it's the tendency of that carriers to occupy the quantum states. And the definition is derived based on the equation 7.
Tell me in your own words, what is Fermi level? What is it? Where is it? Do you really understand or no? Awak borong kakak tua semuanya. Kalau ada yang faham, beritahu.
Based on my understanding during solid state class.
Mhm.
It is the lowest energy for electron occupancy under quantum state.
The lowest what?
Dependent, the lowest energy for the electron to occupy the state, independent of the heat energy. It's the chemical potential energy.
Understand what you're saying, Azim. Let's try Faris Afandi, you.
Energy level is like the energy level that occupied by electron orbital at 0 Kelvin temperature, which means when at the 0 Kelvin temperature, the energy level at certain energy level, the electron is occupied.
Macam-macam jawapan ni. Ada yang 0 Kelvin pula. Let's hear from so Faris Azim, you are from Kuantan, is it?
Yes.
Okay. So saya ingat saya besok baru 3 kelas, saya tak tahu yang mana betul-betul kelas saya, mana tak. So awak from Kuantan. Amirul, you from Kuantan juga? Okay. So everybody, Faris Azim and Muhammad Amirul is not the enrolling in the semiconductor device class. They are our guests here. So but I will treat sama je lah, guest ke tak guest ke, need to answer the question juga. Okay, they are from Kuliah of Science. They are now doing masters, both of you.
PhD.
One PhD. Amirul?
For the ni, I don't get the result yet.
Oh, you are waiting for the result. Okay. So PhD kena boleh jawab semua soalan lah kan? Alright. Okay, good. So we have a PhD. So Fadli tak faham, boleh tanya Faris Azim ni. Okay, Aiman, you tell us, what do you understand about Fermi level? In the, there are many, if you read textbook, there are many definition. But in my class, I just want something that all definitely correct, but the concept is what slightly difficult to understand. So I will try to make it maybe the easiest way, because this is just a elective course. So for PhD, you need to know more lah. After this, you need to know this is basic before going masters or anything. So, but my aim is for even for basic, you at least you have an idea, not just like you just memorize. Okay, Aiman.
Okay, madam. Can you hear me?
Yes.
Okay. So Fermi level is an energy level finding probability of free radius where there is an imaginary line. Okay, so we can divide this Fermi level into two categories, which is intrinsic and extrinsic. So in intrinsic Fermi level,
apa benda Fermi level tu?
the energy level
It is an energy level? You sure? Dia memang ada kena dengan energy level, tapi dia tu
energy Fermi level tu dia supposedly should not have any energy state. Like
energy state tu apa? Do we know what's energy state?
Energy state means that there's energy level, right? That's the same thing where, yeah.
Yes, correct. So you say there's no energy state in Fermi level.
Have any energy state. Yeah, wait.
Wait. Okay.
Fermi level is an energy level finding probability of precarious where there is an imaginary line.
Allah, tak dengar dah pula your internet ni.
Dengar?
Ah,
Okay. So, jap. From what I understand, that is a conduction band and valence band, right? So, Fermi level is in the middle between conduction band and valence band.
conduction band.
Conduction band and valence band.
Yeah, gallium nitride. Okay.
Yeah.
All right. So now okay lah. Okay, okay. Semua jawapan tak salah. Cumanya my question is my concern is whether you really understand or no. Okay, let me share my screen. So, right. So we talk about we talk about last time what is conduction band, what is valence band, right? And I think we talk about the band gap, right? Have we? Yes. What is
Yes, ma'am.
band gap? What is band gap energy? Hannah? What is band gap energy?
It's the wait, sorry. Is the energy it takes for the electron to travel to the from the valence band to the conduction band?
Is that correct, Maisara?
I guess the correct term is not travel, it's excited. Is actually the minimum energy required to be excited, to jump over the band gap to conduction band.
Can you repeat that again?
Minimum energy required for electron to break away from the valence bond to conduction bond. Band. Sorry.
Oh,
Sorry,
jangan
sorry.
bond dengan band. Okay, dalam exam pun jangan tertukar bond, band. Sebab kalau dalam exam you tertukar tu, saya tolak terus, tolak markah. So because bond and band means two different things, right? So you know what is a bond, but you know what's a band. So kalau tertukar tu maksud dia tu salah. So saya kata semiconductor device ni dia very sensitive on the wording that you choose. So it's the minimum energy that the electron needs to jump or excited from the valence band to the conduction band. Hannah, and the keyword is minimum, right?
Okay.
So if the electron get energy bigger than the minimum, then still it can be excited. So this is the minimum. So the band gap is the minimum energy needed. Okay, so we learn about the conduction band, you know about valence band, you know about band gap. Now, so I've told you in the previous class, in the band here, there are a lot of energy state. Now we discussed about this last time here. So in each of the conduction and valence band, there are a lot of energy levels, right? But in the valence band, all the energy levels are being filled with electrons, and conduction band, all the energy levels are filled with holes. Therefore, they cannot move. In order for it to move, the electrons need to go to the conduction band. The hole need to go to the valence band for it to freely move. Okay. Now we understand this is the concept of intrinsic semiconductor, whereby to have a free carrier in intrinsic semiconductor, apa nama ni, the apa saya kata tadi, the carriers need to go to another band to freely move. So that's why we talked last time about this. We talk about this, in intrinsic semiconductor, the number of electrons concentration is the same as the number of hole concentration, because whenever you have excitation, it's always electron hole pair. So one electron being excited, you get one hole. Also being apa nama ni, will be transferred to the valence band. Okay. Now, so that's clear. So now, okay. So if I ask you about Fermi level, where if this is an intrinsic semiconductor, this band gap intrinsic semiconductor, where the Fermi level will be?
Exactly in the middle,
Exactly in the middle. Why?
because the probability to find the free hole and free electron are the same.
Okay, very good. So Fermi level, if I saya mau ucap saya punya pencil. So let's draw. It's intrinsic. So for intrinsic semiconductor, the Fermi level is exactly in the middle because the probability of finding electron holes are the same, right? The probability of finding electron and holes are the same. That's why it's in the middle. So there are many definition in the textbook and everything, but I think the easiest thing to understand about Fermi level is a level to understand the probability of finding free carriers. Okay, free carriers. So if it's in the middle here, without telling, without, in the exam or anywhere you see a energy band diagram, they don't tell you anything. You just, I can give you a piece of picture like this, and I don't I will like, I don't label it anything. You should know this is an intrinsic semiconductor. Okay, with the, if I write here, so intrinsic semiconductor will point to EV. From the internet, you can find out 1.2 EV correspond to which semiconductor material. Okay, because this another thing about the band gap. The band gap is the minimum energy. The band gap is also, I always tell my student, band gap is like a fingerprint of the semiconductor material. So for us, a human being, if I want to know, is this Faris Azim or Faris Afandi, one way of getting to know you is by looking at your fingerprints, right? Our fingerprints are different from one person to another. So for material, semiconductor material, one of the fingerprints of the material is one of the important fingerprints are the band gap, energy band gap. So from the band gap, you can identify which material it is. Okay. So if I just give you for example, I give you just the band gap, you can Google in the internet and go and see all they will have like database. This amount of energy correspond to what kind of wavelength, and therefore you know the material, what kind of material. So if I change this to 1.1 EV, I know this is silicon. Okay, silicon has a 1.1 EV band gap. All right. So okay. So this is important, brothers. When you answer the exam in the final exam, sometimes the question will be, you have to design the semiconductor device. So when designing a semiconductor device, one of the most important thing, or if you want to do anything, any device, LED, solar cell or PN junction or anything, one of the most important thing is to look at the band gap. Okay, you need to know the band gap and you need to know the material. It's extremely important. Therefore, so you need to think of, when you design, you need to think what is the best band gap for your device. Therefore, once you got roughly the band gap, you can then from the database you can find out what are the material that correspond to the band gap. Okay, so by not saying anything, if I look at, so let's say I don't in the exam I just give you this picture, you should be able to tell me this is a silicon semiconductor. Why? Because the band gap is 1.1, and I know it's intrinsic semiconductor, intrinsic silicon, because the Fermi level is in the middle. Okay, so Fermi level is the probability of finding free carrier. So let's say if I draw now another band gap, an energy band diagram. Okay. So now I am drawing the Fermi level. Close to the conduction band. What does it mean?
Maybe conductor.
Huh?
Maybe it's a conductor.
What do you mean it's a conductor, Maisara?
Sorry. I mean, maybe it has high conductivity.
Good try? Not right. Anybody else wants to try?
I think probability.
Fermi level is always about probability. Here also probability.
So for this case, I think the conduction band has high probability compared to valence band for the carrier to occupy the level.
Not accurate. Other people?
Extrinsic semiconductor.
Huh?
Extrinsic semiconductor.
Not specific.
Extrinsic semiconductor.
Okay, good, Aiman. So, so do you want to explain more?
So in an type extrinsic semiconductor, so it introduce a donor energy level. So donor energy level, it close to the conduction band. And how we find the Fermi level? It is because it is always half of the energy level to the conduction band. So normally we don't draw lah the donor energy level, so we just ignore it. Yeah, so that's from what I understand.
Where did you read?
I read from your slide and from video in YouTube.
Okay, good. Good, Aiman. So I see you do your homework. Okay, now, brothers and sisters, so now when we talk about the band gap before, energy band diagram, we say in a band gap there shouldn't be any energy level, right? Right. So only energy level, energy state, you can only find it in the band. So that's why it's called a forbidden band gap. Shouldn't have anything. Ideally, theoretically, it shouldn't have anything there, if it's pure. However, when we dope, this is intrinsic. When we say last time we learned about doping. So we say when we dope it, we add impurities. When we add impurities, the apa nama ni? The matter is no longer pure. So what happens is when we dope, we are actually, so for example, let's say this is silicon. Let's say this is silicon. Let's say this is silicon. We dope it with donor. Can you give me an example of donor material? Donor atom, type of material. You can Google.
Phosphorus.
Okay, good. Phosphorus. Phosphorus. So you add phosphorus to the. So you have a piece, you have a like a what you call this, a pure semiconductor silicon. So what happens is you add donor atom to it, you add phosphorus. Okay, now it's no longer pure. So it become extrinsic. From intrinsic, it become extrinsic semiconductor. And what happens? So how do we translate this in terms of energy band diagram? For like, if you look at my slides, kalau dalam slide tu kan kita ada atom silicon, tiba-tiba ada satu mungkin kat sini, atom phosphorus. So phosphorus ni akan bond dengan beberapa daripada satu extra elektron, because silicon ada 4 outer electron, phosphorus have 5 outer electron, 4 will bond, and you have one extra electron to move around free. Okay, so this is how you see it. For example, you can visualize it in terms of the physical, where is the phosphorus, where are the phosphorus atom will be. Ni kalau physical. So we need to translate this in terms of energy band diagram. Why? Because most of the things that when we explain about the behavior of a semiconductor device, we will be explaining in terms of energy band diagram. We cannot some of the things model ni tak boleh explain. So we have to explain using energy band diagram. So how do we translate this donor atom or doping of the donor n-type to the energy band diagram? So it become like this. Okay, so it becomes like this. When we add a donor atom impurities, we are adding energy level inside the band gap. So it's no longer ideal. It's no longer ideal. So therefore, basically what happens is bila you add kalau dia tu donor means you have extra electron. You will this energy level will be close to the conduction band. Okay, why? Because in order for you to have free electrons, it will be in the conduction band. So, but as mentioned by Aiman, kita start situ. So when we add a donor, we are adding energy level which is close to the conduction band. Fermi level is always in between the two, the energy level and also the conduction or the valence band. So it always be like halfway through here. So but as mentioned by Aiman, normally we don't draw this. If you draw the donor atom, the acceptor atom, our energy band diagram will look messy. So normally what we do is we don't draw this. We don't draw the donor energy level, but we will draw this Fermi level. So, but if the Fermi level is there, we should know where's the donor level. It's always like halfway. Okay, so now whenever you see energy band diagram with the Fermi level close to the conduction band, I don't have to tell you, you should already know this is an extrinsic semiconductor, and not only any extrinsic, it will be an n-type semiconductor. Because why? N-type means you have extra electrons. So what happens is, if we have, what does it mean actually? It means that when you have the donor atom over here, in the donor level here, you have a lot of electron here. So with a small room temperature, this electron can be easily excited to go to the conduction band. That's why at room temperature, we assume each of the donor atom will donate 1 electron. Kan kalau kita calculate and dalam tu equals to, so kata kalau carrier concentration itu, if this in the first year electronics you learn class first year electronics, so you do a calculation, right? So color lain pula so kalau ND equals to 1 kali 10 kuasa 23 per centimeter cube. So if this is the concentration of the donor, the impurities, the doping is 1 times 10 to the power of 23. you here, if you still remember, it means that we are assuming we have electron concentration. We have actually electron concentration of the same. Why we kata macam tu? Sebab we assume one donor atom will give one free electron. So how is that so? Because at room temperature ni kita experiment at room temperature ni. At room temperature, all of the electron over here are being, the excited electron are being excited to go to the conduction band. Okay, but if remember, if intrinsic, right? If intrinsic semiconductor, the electron has to go from here to here. So there's a lot of here when I draw here, saya draw ni exaggerating sikit. ED ni jauh daripada tu, sebenarnya dia sangat dekat. Tapi kalau saya draw dekat kat sini, kalau saya draw dekat sangat tak nampak. Saya exaggerate di bawah sikit. So sebenarnya very small energy. Sebenarnya ni exaggeration. But sebenarnya kat sini je semua tu, very close. So therefore, there's a very large difference between electron to be excited from the valence band to conduction band and the donor level tu kepada conduction band. That's why at room temperature, we have a lot of free electrons when we dope it with donor, because all of them are already being excited. So where are the extra? Because the extra electrons dalam conduction band for n-type, dari mana dia datang? Dia datang daripada sini lah. Daripada impurities donor yang kita add. So dia bukan datang macam tiba-tiba magical, it's already there, no, because of the donor, right? Okay, tapi they are all there, so kita assume semua dah berada dekat conduction band, because the energy needed to be excited from the donor to the conduction band is very, very small, therefore semua can go. Any question up to here?
Madam,
Hmm?
we know that the donor energy level ni dia boleh ada certain level, right? ED1, ED2, ED3 kan?
Hmm?
So how we differentiate kalau contoh dia punya donor energy level ni far from the conduction band, so it look close to the intrinsic punya type, Fermi level. So how we differentiate?
What do you mean? How do we differentiate? What do you mean?
Sebab contoh kan madam kata madam takkan letakkan yang ED ni kan kita takkan lukis kan, so kita just lukis Fermi level. So kalau contoh Fermi level untuk extrinsic tu middle juga, dia bukan middle, dia macam it look like a middle between conduction and valence. So how we differentiate?
So how do we
Differentiate the type, extrinsic or intrinsic?
Oh, okay. Okay, I think that's a good question. Tapi saya twist sikit question tu. For example, okay. Okay, let's say the Fermi level here ni katalah exactly in between this Fermi level. So you're saying, now you are saying ada another Fermi level macam tu lah, Aiman?
Yes.
Kat sini, macam tu. Jadi, to differentiate apa?
Tak, contoh kalau macam extrinsic punya, kalau energy donor tu dia far away from the conduction band, so the Fermi level look like in the middle between conduction and valence kan. So how we differentiate kalau kita nak tahu dia punya type dia, is it intrinsic or extrinsic punya type Fermi level tu. Kan kita tak ada lukis dia punya donor energy level state kan, kita tak lukis yang tu kan.
Yes. Tapi okay, if you go back to the definition, intrinsic semiconductor, the Fermi level is exactly bang on the middle, in the middle. Okay, so if anything other than that, it will be extrinsic. So anything above the middle, it becomes n-type. Anything below, it becomes p-type. Okay, cumanya saya ada soalan tricky untuk awak semua, so tak apa, kita habis n-type, p-type, saya ada soalan untuk awak nak cuba fikir sikit. So now, okay, now we understand. Now we understand what Fermi level is and where the Fermi level is for n-type. So let's say, so if I'm going to draw this for the p-type, So the Fermi level will always be closer to the valence band. If any time you see this is p type, this is n type, extrinsic. So anytime you see a Fermi level which is closer to the valence band, you know already this semiconductor is a p-type semiconductor. Okay, let me give you another saja now. Test you. So if I give you I draw this conduction band, the valence band. Saya draw ni, betul saya draw sini sikit. Ni AF. So kita A, B. Ni material A, material B. So what's the difference between material A and material B? Nampak tak? Saya draw tak? Okay, mungkin saya kena draw lebih accurate. Nanti awak kata ni material berbeza. Okay. So saya copy this. Okay. Exactly the same, huh? Exactly the same. So except for now, saya tukar level ni. Okay, what's the difference between material A and B?
Lower concentration of
Which
dope.
one have a lower concentration?
B,
Why?
because the Fermi level is much closer to intrinsic punya.
Or you say Fermi level is further away from the valence band, right? Okay, because the reference is always the band. So here, so one important thing. So one thing is we know, number one, where if the intrinsic in the middle, you know it's intrinsic. If the Fermi level in the middle, you know intrinsic. If it's closer to conduction band, you know it's n-type. If it's closer to the valence band, you know p-type. But one thing is the level where it is in the band gap. If it's closer to the valence band, it means that the concentration is higher. Okay, so if any Fermi level closer to the valence band, the concentration of the acceptor atom over here is higher than material B. So here, if I draw like this and n-type the same, if I have another Fermi level which is closer to the conduction band, I know this yellow one has a higher concentration of the donor atom. So sometimes in the exam, I will not like give you clues. I don't write, I will just draw. So you should know that what's the difference. Sometimes I will give you in the question, draw me two material of this, and sometimes I will say it's a hetero structure. After this, I will explain what's hetero structure. So you need to, when you draw, you need to show the relative difference on the carrier concentration. So then I will check how it's relative. I don't say you have to measure 2-3 cm. It should have to be accurate. It just show that this should be higher, further away from the valence band as compared to this one. Okay, any question up to here? Hana? Soalan Hana? Dengar tak ni?
Madam, when we put a donor atom, right? Do we always put it at the valence band? Like from relative to the valence band?
Good question. Fadli, answer.
Can you repeat, Anna?
Huh?
Repeat.
Repeat.
When we have a donor atom, is it always relative to the valence band?
Fadli jawab. Payah sikit soalan ni ke? Kau faham tak soalan tu?
Nope.
Ah, dah kau tak faham, tanyalah dia. Jangan senyap. If you don't understand question anything, so ask her question if you don't understand.
Can you repeat again?
Okay, so when we have a like tadi, we have a donor of an N-type, right? Phosphorus.
Hmm.
So the energy donor level, it rises from the valence band up over the middle, right? So the donor level is above the 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 Fermi level, right? So when we don't have a donor of a p-type, is it relative to the valence band or not? So like, do we rise it from the valence band or we do it from the conduction band? So that's what I'm confused for.
I guess it will depends on the valence band, because for p-type it will relate to valence band, because the Fermi level for p-type is below than the middle line for intrinsic semiconductor Fermi level. That's my answer. I don't know if it's right or wrong.
Sebenarnya saya tak faham sangat soalan Hana tu. Apa benda soalan awak sebenarnya?
Like when we have an N-type donor, the
donor
band is closer.
Memang donor tu
It's closer to the conduction band,
Okay.
right? So
You know why, right?
yeah, because we're adding electrons.
Yes, you get
So
free
when we
electrons in the conduction band.
So when we add holes, where is the donor punya energy level?
Donor ke acceptor?
No, sorry, acceptor energy level. Sorry, acceptor.
Okay.
That's what I'm sorry. My words.
Okay, now I think I understand why you ask this
Okay.
question. Sebab I think I understand why you ask this question, because
Because I'm
here,
like, where is the acceptor band? So I mean, yeah, sorry.
so here because I draw the ET here, right? So
Yeah.
tapi bawah ni saya tak draw. Okay, so saya assume awak dah faham, saya tak apa. So sebenarnya kalau saya tak draw ni, memang dia kat sini dia always 50%. Dia Fermi level tu dia memang halfway. You know, whenever I draw a Fermi level, halfway between this will be this green line will be the acceptor atom.
Okay. Okay.
Okay, it's always 50% the Fermi level between the level state. Okay.
Okay.
So all right, good. Any other question? Anybody else? Everybody understand? You sure? Make sure if I ask you question after this, you can answer. Okay. Right. So now we settle about Fermi level. You know about the N-type, P-type. Apa lagi yang saya suruh cari? Alman?
What is band gap energy band diagram, Fermi level, doping, dopant, donor, acceptor. Yang atas tu dah settle lah.
Tu je?
Atas tu what is electron, holes, carrier, proton, neutron, nucleus, what is electron hole pair means, what is semiconductor material and type of semiconductor.
Okay. Okay, so we also talk about the apa ni? We talk about last time on the elemental and compound semiconductor done. So kita ke basicnya. It's time to think. Okay, so apa lagi basicnya? Saya buka slide saya sekejap. Slide saya tu ada apa? Can think of any question, you can ask me now.
Madam,
Mhm.
For the low concentration takeoff of the Fermi level is greater, I didn't understand the low concentration of what exactly.
Macam mana? Can you repeat that again?
The low concentrations, I didn't understand the concentrations of what.
Ah, okay. Maisara answer.
In my opinion, when we are talking about concentration, we are actually talking about the amount of carrier. It's whether the electron or holes. So is that really answer your question? So when in n-type, we are talking about the concentration of electron. The electron is apa? The amount of electron is usually higher than the holes. When we are talking about the concentration
Macam
in
mana?
p-type,
Repeat.
when we are talking about n-type, the
Uh-huh.
concentration of electron carrier is higher than the holes.
Okay.
So that means it has high conductivity. When we are talking about
High
in
conductivity.
p-type,
Kalau banyak hole tak ada high conductivity.
low, it's low conductivity.
Really? Are you
I
sure?
don't know.
I don't know. Titi pun tak tahu. So what? So if your answer is correct, why we dope with p-type then? Why become p-type? Why we dope to become p-type?
We do p-type.
Ah, kenapa kita buang duit dope with become p-type? Online get ready to answer.
Okay, when we I tak ingat ada condition ni. I don't know, madam.
Minta tolong Aiman. Ha.
Aiman.
Boleh tak Aiman tolong ni ha?
Yang mana?
Yang mana?
Concentration.
Yang tadi tu p-type tu dia kata lower kalau n-type maknanya dia high conductivity, high conduction ke apa benda kata nak pakai tadi. Nak conductivity. Okay, kalau p-type lower conductivity. Betul kan Aiman?
Untuk elektron ke untuk holes?
Oh, ada soalan lain pula untuk elektron ke electrohole. Ha, jawab Miss Sarah.
Kalau p-type dia ni ke Aman? Entahlah.
P-type dia concentration dia related to holes because memang p-type tu sendiri extra holes, right? So concentration dia depends on the holes lah, p-type.
So, kenapa kita jadi p-type? Kenapa kita tak buat semua n-type je kan senang je tu. So conductivity naik sebab n elektron je. Aiman? Do you know? Interesting. Bagus soalan siapa tadi? Kamalia yang tanya dia. Dia membuka Pandora box. Dia membuka soalan-soalan lain yang now saya ingat ke benda tu clear, rupanya tak clear. Okay. Faris Afandi, jawab Faris. Makan apa?
I think the conductivity not depends on electron only. But both have conductivity. It depends on the concentration of the carrier at it depends on the concentration. When it n-type, the concentration is electron, so electron will conduct
Anda ni confused dah saya dah ni. Macam mana sekali lagi?
So when the n-type, the concentration of electron is more than holes. When it's p-type, the concentration of hole is more than electron.
Yalah, memang kita semua tahu dah soalannya Faris tadi. Dia kata p-type, lower conductivity. So what? So conductivity, is that right?
I think no.
You say no, then why no?
Because conductivity. because both electron and hole conduct electric.
Carriers. So then the next question will be what is current? Conductivity means the higher the conductivity, the higher the current is, right? So now my question is what is current dalam semiconductor? Tak boleh jawab ni, kita memang tak boleh go on lah, move to the next stage.
Flow of carrier.
Flow of
Flow
carriers.
of charge, isn't it?
Flow of charge.
So-
Charge tu apa in semiconductor?
There's the positive charge, which is the holes, and the negative charge, which is electron.
Okay, so we see carrier lah kot. Sekarang ni kita guna perkataan carrier. So flow of carriers, free carriers. When we say carriers here, of course, it's free carriers. Bound carriers, we talked last time, doesn't mean anything to us because it tak buat apa-apa. So when say free flow of carriers saja betul ke? Is a current. Amirul?
Flow of free carriers.
Flow of free carriers betul. That is current, betul ke?
Flow of free carrier current. Flow of free carrier current. Flow of free carrier electron dengan hole lah.
Yeah, is that right? Betul ke? I'm asking you. Is that current?
Oh, flow of current is flow of carrier macam tu.
Yes, is that statement right or wrong?
Flow of carrier right.
Okay, who says right? Raise your hand now. Who says? Then I will ask. I want to see everybody answer. Is the statement correct? Current is flow of carriers. Raise your hand. So tak raise tu you answer no lah kan. So my Sarah seorang je, my Amirul say yes, right? Dua orang je. Orang lain? Jawapan dia no. You sure? So semua orang ni no Okay, Hana kenapa no?
Oh no, I meant yes.
Apa? Ya Allah.
I meant yes because I thought it's like angkat tangan kalau yes.
No, angkat tangan kalau yes. If the
Oh.
statement is correct, raise your hand.
I think it's correct, but something's missing. But I'm not sure what the thing is.
Oh, okay.
It's like half right, but I don't know what the other half is.
Okay, what is the other half? So who knows? Anybody?
Is it the net flow of carrier per unit time?
Okay, what does net means?
The rate.
What does rate is per unit time? What's the net means?
Number of carriers.
No, not exactly. I will tell you why. So I will give you example why in semiconductor device, every statement is very sensitive. Sebenarnya sangat sensitif semiconductor ni. So maknanya awak kena hati-hati lah. Especially talking to an expert. When you talk an expert about semiconductor device, kalau awak cakap dengan orang tepi jalan ke, lecturer engineering tapi bukan semiconductor expert ke, dia tak kisah. Tapi when you talk to a person who ada hidup dia 20 tahun hidup dengan semiconductor device, so dia memang dia tahu perbezaan antara belian dan permata lain, you know. Ni sebab kita dah tengok tiap hari. So jadi kita tak boleh terima ini bukan belian. Orang kata belian, tak, bukan belian, dia adalah kategori lower dan tidak sama dengan belian sebab ni. Okay, so let me give you an example. So this, if I take this piece of, let's say this is a semiconductor, this is silicon, seketul ni is there any current flowing now? Ada ke tak ada?
No.
Buka lah mic tu, No.
No.
Okay.
No.
Ada orang kata ada ke? Tak ada kan? Kalau tidak saya kena electric shock lah. Okay, good. So next question is, in this piece of semiconductor, is there any carriers flowing?
Carriers flowing. Net carrier tak ada tapi carrier ada.
Okay, so what do you mean by that?
Dia macam net force dengan tak net force dia lebih kurang macam tu. Tapi dia nak describe dia ni.
Apa?
Ya. Kalau
Okay, kita tunggu kejap semua.
net carrier net. Dia net carrier tu kita bila dia tak ada net carrier dia equilibrium, so no flow.
So you say there's no flow. Is there any movement flow of carriers ke tak ni?
Kalau in equilibrium, no flow of carrier.
Is that right, Fadli? Sebab saya, one thing when I teach this class, I want you to think. Semua benda dalam fizik ke, semiconductor ke engineering, semua benda dia logical tau. Dia tak ada benda-benda yang jump, tiba-tiba kita kena hafal. Tak. Dia kalau you want to really score ataupun really understand, you can understand through logic. Dia macam relate, dia macam dia tak ada tiba-tiba jadi macam tu. Kenapa equilibrium tak ada pula benda flowing? Does it make sense or no? Fadli?
I think what Amirul say is correct.
Apa? Amirul
I
is
think-
correct? Ha?
Yes.
Apa yang correct?
Yes. When there is when it is in equilibrium, there is no flow.
My Sarah, you agree? Ni saya pegang semiconductor ni at room temperature. I'm in room temperature now.
What I understand when at equilibrium,
Uh-huh.
it has equal carrier concentration.
What do you
That's only I
mean?
understand. I'm not sure about the flow. Whether
Kita
it
equal
has,
carrier concentration pula ni.
I'm not sure whether. I'm not sure whether there is a flow or no. Because when we are talking about the flow, there must be energy supply and will be energy that move the carriers. So I'm not sure whether
Okay, so that's why I said now I will demonstrate to you why I said the terminology is very sensitive as semicon. Okay, let me share my screen. Okay, I will draw. And that's why, sometimes you'll be shocked at looking at your quiz, why you get very low marks. Because of sometimes the terminology. So, but you need to understand why terminology are like that. So, for example, tadi kita draw macam ni kan. Tak straight. So this conduction band, this is valence band. So this is a band gap. At room temperature, there will be some electron that will be able to be excited to so that's like silicon at room temperature. There will be electron that will be excited to go to the conduction band. There will be hole that will be excited to go to the valence band. Okay, therefore, bila electron ni dekat sini, apa akan jadi dekat electron tu bila duduk dalam, when they are here? Electron ada color. So here, apa pun ada kat sini kan? Oh, kita color lain lah. So that's sebab dia free kan. Let's color dia purple sebab dia free. So this electron here, I told you before, right? In the conduction band, there are a lot of empty states. Therefore, this electron can go and move to any empty state. Misalnya saya ceritakan dulu macam dalam classroom. Bila classroom tu ada tempat kosong, kita boleh pergi kat situ, we can occupy tempat kosong, ikut suka kita pergi untuk duduk occupy tempat kosong. Macam tu juga elektron ni, dia akan move. Bila dia, walaupun ni what I'm drawing here is a piece of semiconductor like this at room temperature. So maknanya kat room temperature ada free carriers, yes, ada free carriers. However, the free carriers are moving but in random. Dia ikut suka nak pergi mana. Ikut suka dia nak pergi mana. Kat hole bawah ni pun dia pergi juga, dia bergerak je. It's moving. But dia moving randomly. Therefore, in the end, there's no net flow of carriers. Sebab tu net tu penting. Net tu, because net ni maknanya dalam random dia tu ada juga yang beberapa yang pergi daripada satu arah ke satu arah, right? From the positive side to the negative side or negative side to the positive side. So when say net movement tu, dia ada macam kalau buka textbook lah, dia akan draw macam ni. So dia ada satu arah yang ni, walaupun ada yang satu dua yang akan pergi merata-rata ikut suka dia, tapi beberapa akan pergi pada satu arah. Majority maybe lagi banyak this net flow, therefore the higher the current. So current is net flow of carriers per unit time. net flow of carriers per unit time. So dia ada so lagi kalau pada masa yang sedikit banyak carriers flowing, lagi tinggi the current. So therefore current are being influenced by the concentration of the free carriers, which is doping ni lah tadi. So kalau doping dia tu high, it means the current will be higher, right? Kalau electron concentration dia higher, the current will be higher. If the whole concentration is higher, the current will also be higher, because in semiconductor there are two types of carriers that contributes to the current. Two carriers, satu electron and satu hole. So kalau hole punya concentration tinggi pun increase the conductivity. Okay, Mas Sarah? Okay, so that's why. Tapi dia current in the end kita biasanya masa kita buat electric circuit, masa kita do engineering electronics semua, we just calculate the current. We don't care whether it's electron current or hole current. Tapi in semiconductor there are two types of current. You have electron current and hole current. And the total current will be the sum addition of the whole current and the electron current. So dua-dua ni contribute to the current inside a semiconductor. Okay. So maknanya bila awak calculate awak calculate yang electric circuit, electronics dulu tu, calculation tu you take, baby kata current I tu sebagai current, it is a sum of both the electron and whole current. Tapi now we going very, tu saya kata dalam some other device we going very detail. So current tu kita split dua. Kita ada electron current, kita ada hole current, because that is how do you get current in semiconductor material. Okay, is it clear, my Sarah? Okay, everybody else, do you have any? Is it clear? You all have any more question? Bukan my Sarah tanya soalan tadi. Siapa tadi? Kamalia, apa?
Yeah, me.
Kamalia, is it clear?
Yeah, okay.
You sure?
Yeah, sure.
Okay. So I have a question. Do you all have question tak? Kadang saya nak tanya soalan ni. You better have question. Tak boleh jawab ni, jaga awak. Sebabnya saya suruh awak tanya soalan, awak tak nak tanya. Any question?
Prof,
Yes.
I have one question. Can
Yes.
we answer the conductivity in terms of the reduction of band gap?
Reduction of band gap? What do you mean?
When you introduce dopants, the what you can say, the band gap is filled by the donor level, right? Donor and acceptor. Which
Band
means
gap is filled in with donor and acceptor level. Okay. Betul?
then somehow it changed the band gap energy from the intrinsic semiconductor to extrinsic semiconductor. The band gap energy would change, right?
Okay. Okay, good question. The answer is it depends on the the concentration of the doping. So normally untuk level kita orang kanak-kanak dekat for elective ni kan, My Sarah, kita kanak-kanak level lagi, we assume there's no change, negligible. But I know if you do a simulation also for your master, your PhD, it has an effect. But that is at very high doping concentration. At normal doping concentration, we assume is negligible. It doesn't change the band gap. Okay. Alright. So jadi tapi yang tu saya tak cover dalam kelas ni sebab kalau tidak kasihanlah mereka akan lagi confused. So saya try nak yang secondary third level tu extra. Tapi it's okay to ask question. From here brothers and sisters yang lain tu ilmu ni sangat interesting ilmu Allah ni. Kita kan saya cerita dulu belajar masa first year electronics tu kindergarten level. Bukan 5 years old level. Lepas tu darjah first year tu baru kindergarten. Gini kita baru nak masuk tingkatan 1 punya level lah. So dia ada tingkatan 5, dia ada universiti, ada banyak lagi tingkatan ke atas. So lagi kita buat research in the area, lagi you will find out wow, many things are not like it is supposed to be. Why? Because Sebab itulah because of that, that's why ada research. Kalau ilmu tu dah sampai kat situ or everything you know, there will not be research. Research ni sebab bila kita push the boundary, lain pula dia punya sifat dia. Push lagi, lain pula sifat dia. So that's why there always be research. Tapi we always need to know the fundamental lah, minimum tu kena tahu. Kalau darjah 1 pun tak faham, macam mana nak faham darjah 6 lah. So jadi so sekarang ni kita tengah nak faham bukan darjah 1. I will say that mungkin I will say tingkatan 1 lah sekarang ni. Okay. So alright, good. Any more question? Tak ada? Okay, tak ada. Saya tanya soalan ni. Okay. So my question will be, katalah sekarang ni saya ni kita ni kadang-kadang kita engineer, we like to do experiment, right? We are scientists, we like to do experiment. Now I have a piece of semiconductor material. Ni pure, let's say silicon lagi lah, kita hidup kita mudah sikit, silicon 1.1 EB. And I dope it, now this is pure semiconductor. So saya decide, why not I add donor atom of 1 times 10 to the power of 21 per centimeter cube. Okay. So bila saya add donor atom ni, apa akan jadi ke saya punya material ni, Kamalia?
N-type.
Okay, it become N-type. Okay, then after sometimes I feel like, okay, maybe I should do more experiment. I will add acceptor atom. Ni dah jadi N-type, tapi I put more of acceptor atom of 1 times 10 of power 22. What will happen to my my material here now? Aiman ke, Amirul ke?
P-type, madam.
Huh?
P-type.
Why P-type?
Because they're extra hole.
So what happens to the donor over there? So okay, if it becomes a P-type, okay, good, the answer is right, it becomes P-type. But what is the carrier concentration inside my semiconductor now? My P because kita ada ini dulu, kita ada N, kita ada P. What is my whole concentration?
10.
Huh?
10
10 what?
centimeter cube.
Huh?
1 times 10 power of 1 centimeter cube.
Why?
Because the donor fill the holes of the dopants.
Can you repeat that again? Louder.
Donor fill the acceptors punya holes. Is
Donor
it?
field acceptance punya hole. What do you mean by field?
The extra acceptor electrons only 1 times 10 compared to the donor punya concentration.
Okay, so everybody you can go and Google carrier compensation. So sometimes pernah tak masak pernah Hana, awak suka masak tak Hana?
Saya tolong masak je.
Kalau masak kari tiba-tiba termasin, apa awak buat apa dengan kari tu?
Terlalu masin.
Terlebih masin.
Tambah air sikit.
Bagus. Tapi kita tak nak cair ni. Kalau cair tak best. Lepas tu kita buat apa?
Tak. Tapi tak asam sangat, nanti masam sangat pula.
So kita mungkin tambah, for example, kita nak balancekan dia masih kita tambah gula. Right? Kita akan tambah gula. So therefore, in the end, bila kita tambah gula tu, rasa kari kita kan rasa masin lagi ke tak?
Tak.
Rasa tapi tak semasin tu kan? And then dia akan balance, dia mungkin rasa gula manis sikit. It depends banyak mana gula kita letak, right? Right. So sama juga dengan semiconductor ni. Bila kadang-kadang kita doping, betul kita tengok alamak doping ni terlebih macam sebab bila kita do eksperimen, bukan eksperimen, kalau real dekat dia punya apa kataan tu, MBE ke apa, dia punya mesin, apa nama mesin tu, tak ingatlah pula tiba-tiba. Siapa ingat nama dia? Yang bila kita nak dope ni, dia bergantung jenis material tu macam mana. Bila kita make the doping process, sometimes it depends on material yang kita nak dope tu, makna the semiconductor material kat bawah kan, and it also depends on the dopant. It depends on the dopant. Sometimes kita nak dope tu, dia akan bergantung pada temperature, pressure yang kita nak letak dia, so dia masuk dalam kita punya semiconductor. So kadang-kadang kita tak boleh nak control precise dia punya temperature dan pressure tu. So jadi kadang terlebih garam. So kadang terlebih donor. Therefore, so kita nak jadikan dia tu, tapi kita tahu resepi dia in the end, semiconductor ni kita nak ada doping concentration banyak ni. Right? Banyak ni. Tapi kita dah terlebih yang ni. Therefore kita boleh tambah dopant yang opposite tu, and dia panggil doping compensation ke? Bukan carrier compensation ni, doping compensation kot. Saya tak ingat exactly nama dia apa. Doping compensation, dia compensate. And therefore kita in the end kita akan dapat yang kari yang kita nak tu lah. Okay, so it means that kalau macam gitu, then my next question will be, how does that reflect to the Fermi level? Kalau saya buat case macam gini saya suruh draw the Fermi level, dia akan jadi macam mana? So in the end, the Fermi level is just when you draw the Fermi level, you draw the overall Fermi level. Awak tak draw, kau maknanya you kena calculate dia which not cover in this course. All calculation will not cover in this course. Dia ada calculation carrier doping compensation ni ada, awak boleh buka textbook, dia ada equation there. So if you have to do it when you are working, just buka textbook, dia ada equation, tak susah pun, dia suruh letak ND, letak NA, then you know what's the final carrier concentration. From the final carrier concentration, you will know whether it's acceptor or it's the donor, then you draw accordingly of the Fermi level. Awak tahu, then awak letak dia dekat Fermi level kat mana, dia lebih kepada donor, awak draw dia dekat connection band. Kalau ni kat valence band. Okay. Any question? Kita ada 5 minit lagi. Ada question? So, okay. So, tak ada question lah. Let's look at my slide. So, slide saya tidak boleh dipercayai I made already disclaimer. So to those who just join, don't trust 100% my slide. Kadang-kadang saya saja letak bom-bom di sana supaya you will come to class. So we looked at this periodic table before, mostly in the group 4 and group 3-5. We talked about this before. And if it 3-5 dipanggil 3-5 semiconductor, 3-5 semiconductor or group 4 semiconductor. Okay. And normally group I need to talk about, Aiman jot down next class, remind me to talk about direct and indirect semiconductor. Okay. Saya lupa nak suruh. Tak pun, better ya out semua cari sikit. Direct and indirect semiconductor, apa benda tu. Okay. Right. Okay, then ni saja predictable, so macam-macam kita boleh buat dengan anugerah Allah bagi kat kita. Ni semua material ni Allah yang create. Kita ni cuma jumpa cari yang gunakan dia untuk kegunaan manusia. Sebab as our part of being a khalifah, right? So we are supposed to study all this and make use of it untuk kegunaan manusia supaya manusia boleh beribadah pada Allah. Okay, so now we talk about before conductors, insulators and semiconductor. And the difference is in the conductivity and resistivity. So semiconductor is always in between. If you dope it, the conductivity will increase. If you dope the semiconductor, the conductivity will increase. Resistivity will decrease. Yeah. Okay, this is also a very important graph. Ni memang okay. Final exam definitely keluar setiap semester. So saya beritahu dah lah, tu pun kadang sudah tak boleh jawab, saya pun tak tahulah. Walaupun saya beritahu tiap-tiap kali, tapi of course lah, dia benda ni dia keluar macam ni, tapi soalan tu saya akan twist lah soalan tu. to check whether you understand or not. So basically this is a very important ni. So next class remind saya direct, indirect, and then remind to find also you try to find what is lattice constant. Lattice constant tu apa? Dan after kita tahu lattice constant tu, kita akan tengok dekat we will study this graph. Apa benda ni? Then ni graph ni basically is a map of the sum of the semiconductors with their lattice constant and band gap. And we'll discuss kenapa graph ni penting. Okay, dia ada group. Group 2 pun ada ke 2, 4. Okay, next. Ni semua kita dah cerita ni. Zinc blank ni saya tak cover sangat macam mana dia punya apa nama ni type tu. Apa lagi? So electron holes convert to the current. Ni semua kita dah cover except for I didn't cover in terms okay. Next time remind me Aiman talk on that and that effect of temperature to carriers in semiconductor. We'll cover effect of temperature to the carriers in semiconductor. And also because bila kita cerita effect of temperature, kita akan tengok graf ni juga. Graf ni pun penting kat, kadang keluar definitely if not final exam dia keluar dalam quiz lah. Okay. Doping. Okay, doping kita dah cerita. Ni interstitial substitutional ni. Okay, another thing remind me, we need to talk about defects. Okay, Aiman, we need to talk about defects in semiconductor. Ini sangat penting untuk FYP saya juga. So make sure you don't miss the class. Okay, defect in semiconductor. Okay, ni semua ni boleh baca lah. Sector ni semua ada dalam Google Classroom lah. Alright, so kalau kita habis tu, kita habis introduction. Tapi tak boleh juga saya lepas tu kita kena talk about, habis ni kita nak talk about mobility sikit. Mobility dengan, tapi tu slide nombor 2. Kita cover yang tu dulu for next class. Okay. Okay, any question before we close the class today?
Madam, yang untuk soalan next tu, mechanical stress, madam nak cakap juga ke?
Mechanical stress? Kenapa awak tanya soalan tu?
Sebab tu macam berkaitan dengan defect ke?
Okay. Let's talk about stress and strain.
Stress and strain.
Mechanical stress and strain in semiconductor. So don't blame me, Fadli, Aiman yang suruh masuk dalam syllabus. Just kidding. So apa nama ni, yang tu kita, benda tu penting untuk quantum. Satu lagi tambah kita, we need to know about quantum well and quantum dot. Quantum well, quantum dot. Heterostructure. Semua ni awak kena cari. Okay, you also need to find about, ni semua basic ni. Heterostructure, homo structure, heterostructure, homojunction, heterojunction. Okay, sebab kita kena tahu tu dulu sebelum quantum well, quantum dot ni. Lagi ke boleh tertinggal lah. Banyak lagi sebenarnya. Nampak. We need to know about generation and recombination. Generation, recombination, lepas tu so we will talk about defect. Dia ada apa nama ni, we need to talk about tunneling tak apa, kita cerita tunneling bila masuk PN junction nanti. Cukup kot dulu yang tu. That one will cover one class kot. Okay, if you go and Google a bit, Google a bit about that. Make sure now I want you to come to class with some understanding and ask me question. Okay, so it's a game. You ask me question before I ask you question. So sebelum saya tanya soalan, eloknya awak tanya, okay madam, saya ada soalan dulu. Then awak selamat lah. Kalau awak senyap, so maknanya saya akan tanya awak soalan. So kalau nak selamat, awak tanya saya sebanyak soalan yang boleh. Okay. Alright, I think that's good. I think that's all for today. Happy. Dalam Islam tak ada Nabi Muhammad SAW dan sahabat tak pernah celebrate Maulidul Rasul. Kita celebrate birthday kan, Hana bersungguh celebrate birthday. Nabi Muhammad SAW kekasih Allah ni, dia tak pernah pun celebrate birthday dia. Kenapa Kak Malia?
Tak tahu lah pula.
Tak tahu. Faris Afandi, kenapa rasa-rasanya? Ke sebab lelaki tidak pentingkan birthday ke apa jawapan dia?
Semakin kita tua, semakin dekat dengan kematian.
Apa dia?
Semakin kita meningkat usia, semakin dekat dengan kita dengan kematian. Tak tahulah.
Sebab tu ke Nabi tak celebrate?
Sebab dia tak tahu. Lain konsep.
Lain pula. Okey. Fadli, Ustaz Fadli, tolong jawab sikit UIA student ni lah. Ustaz Fadli dah first year ni, nak lepas grad ni orang kata, oh UIA, Masya Allah, brother. Can you explain? What?
Aiman? No.
Okay. Aiman. Ustaz Aiman pula, Ustaz Fadli dah pas ke Ustaz Aiman macam mana Ustaz? Aiman, do you know?
Tak tahu itu.
Amirul?
Kalau birthday, macam birthday mak saya sambut sebab seronok. Barangkali sama macam tu lah kot.
No, my question is why Prophet doesn't celebrate their own birthday.
I don't know.
The sahabat also didn't celebrate. Faris Azim.
I think because they bersyukur every day. So dapat hidup.
Macam mana?
I think because sebab Nabi ajar untuk bersyukur every day sebab dapat hidup lagi.
Okay.
Not just birthday.
Okay lah, ustaz-ustaz dan ustazah-ustazah sekali. Ada ustazah nak jawab, ustazah? Ada. From the history of Islam, until very far from since the Prophet death, there's no celebration of Maulidul Rasul. Only recently baru ada. And if it's important, of course Rasulullah will the first one do it, right? And the Sahabah will do it, right? So madam ni apa ni, Wahabi ke tiba-tiba? So no, I'm telling you what's in the history. Okay, so I'm not against. It's just that we should know. So in Islam, whatever Rasulullah SAW did is the important things. Rasulullah tak ada masa nak buat benda tak penting, and tak penting, tak significant dan tak important. So to Rasulullah SAW, celebrating his birthday is not important. The important is for us to worship Allah. Kita sibuk, minta maaf lah, sibuk celebrate ni, birthday ni. Tapi in the end, kita tidak buat pun yang Nabi suruh buat. Apa dalam Quran Allah kata, in kuntum tuhibbunallaha fattabi'uni yuhibbukumullah. Apa maksud dia, Faris Afandi? Tak tahu. Allah Ustaz. Okey, orang lain, Ustaz lain ada boleh tolong? In kuntum tuhibbunallaha fattabi'uni yuhibbukumullah. Sudah UAE, jangan, kita kena, jangan buat saya malu cepat Kuantan pula, Kuantan kita lawan Gombak, lawan Kuantan. One day kita buat kuis dah, tengok siapa menang. Kuis agama. Itulah Samikon. Menyesal aku masuk kelas Samikon. Okeylah. So ada nak jawab? Pernah tak dengar ayat ni? Yang awak ni semua tak tengok ke yang viral fattabi'uni tu? Apa ni madam? Kita orang tak pernah dengar. Okay. Awak tengok apa pun saya tak tahu. Dia ada yang kan ada series yang panggil fattabi'uni. Yang maksud dia, nantilah kalau saya jumpa saya share dengan awak. Very interesting. Orang Arab buat. Ayat Quran tu ayat Quran. Allah kata, kalau kamu in kuntum tuhibbunallah, kalau kamu semua, kita semua ni cintakan Allah. Cinta tak Allah, Aiman? Tak berani tak jawab tak kan. So of course cinta. Kalau cinta Allah, apa buktinya? Kalau perempuan dia tanya macam tu, kalau kau cinta you love me, what is your proof? Kalau Allah akan tanya, If you love Allah, what is the proof? Payah nak jawab pula. Saya ni tak baca. Ha? Macam mana?
Dia
Ha?
macam mana kalau kita cinta Allah?
What is your proof?
Just kita buat semua rukun Islam. Yang ni lah, kalau macam haji kan ikut kemampuan kan. So kita follow rukun Islam and saya rukun iman semua. And kita buat lah sikit macam apa?
Sikit.
Extra kita, kalau kita cintakan Allah lagi, kita buat lah qiyamul lail semua.
Okay. This is not what I say. This is what Allah said in this ayah. So remember it closely. Bukan Ustaz kata, bukan Prof Azlin kata, ni Allah the one who created the universe in the Quran. In kuntum tuhibbunallah, jika kamu cintakan Allah, fattabi'uni yuhibbukumullah. Kamu ikutlah aku. Ayat ni Allah rakam dalam Quran. Kalau kamu, Nabi kata, kalau in kuntum, kalau kamu cintakan Allah, fattabi'uni, ikutlah aku tu Nabi. Fattabi'uni yuhibbukumullah, dan Allah akan cintakan kamu balik. Sebab bila awak bercinta, awak nak one way ke bercinta? Fadli? Awak nak ke awak cinta seorang-seorang tu tak cinta awak? Tak, tapi tak apa madam, saya tak kisah lebih lautan api ke. So macam, no, yelah memanglah tak kisah masa gila tu kan, tapi masa gila cinta, tapi sebenarnya awak nak reciprocal. Kita manusia macam tu. Tapi Allah pun tahu, Allah jawab dalam ayat yang very simple ni. In kuntum tuhibbunallah, kamu betul lah cintakan Allah ni. Fattabi'uni, ikutlah aku. Nabi kata, ikut, fattabi'uni, ikut. Ittabi' ni maknanya kita ikut every single thing yang Nabi buat. Fattabi'uni yuhibbukumullah. Allah akan cintakan kamu. So bukti cinta pada ni based on dalil lah. Kalau saya kata, saya pun nak evidence kau cakap apa. Quran, hadis, Islam pun you need to have evidence, you will say something. So the evidence of saying apakah proof that you cinta Allah adalah, proofnya ialah kamu mengikut Rasulullah sallallahu alaihi wasallam. That is tanda cinta pada Allah. And so sebagai hari Maulid Rasul tazkirah sekejap ni, ialah kita tanda cinta Nabi, bukannya kita belau buka social media everything. Yalah, it's good, tak salah. Tapi sebenarnya paling penting ialah kita kena ikut Nabi Muhammad SAW, selawat pada dia. Itulah tanda cinta kita kepada Allah SWT dengan ikut Nabi. So sahabat-sahabat sangat clear benda ni. Dia tak celebrate Nabi sebab benda tu Nabi tak celebrate. Benda tu tak penting sangat lah. Kan nak kata, madam ni tak cinta Nabi, tak boleh kata ke Maulid Rasul. Boleh, up to you. Tapi yang paling penting, lebih penting ialah kita ni follow apa yang Nabi suruh. Nabi qiyam tiap-tiap malam, kita qiyam tak? Oh tidak, tak tahulah berapa last time saya qiyam. Baca Nabi istighfar more than 70 times a day, kita buat ke tak? Kita bila every time nama Nabi Muhammad sallallahu alaihi wasallam sebut, kita sebut tak? Selawat ke tak? That is actually kita cinta Nabi. So sekarang ni on hari ni, so kita reflect lah diri kita, adakah kita and kalau kita cinta somebody kan, kita kena tahu pasal dia. Bolehkah awak cinta somebody? Kadang-kadang kita tahu everything pasal orang yang kita cinta tu. Pasal Nabi Muhammad SAW, how much do you know about Prophet Muhammad? How much do you know? If I ask you, who's the daughter of Prophet Muhammad SAW that married to Uthman? How many daughters of the Prophet Muhammad SAW that married to Uthman bin Affan? Tak boleh jawab, dan macam mana cinta? Macam kata usah bercakap tentang perjuangan jika kita tidak, macam itulah, ni usah bercakap pasal cinta bila kita sendiri pun tak ada proof pada cinta kita. So maka silalah baca sirah ya, semua orang, sebab kita tu tanda kita sayang dan cinta pada Nabi Muhammad SAW. So daripada kita duk baca tak apa-apa, tak tahulah awak punya siapa yang awak baca lah. Kalau tak baca apa-apa pun saya tak tahu. Kata awak sibuk main game ke apa ke, I don't know what do you do with your life. Rather than doing that, go and read about Prophet Muhammad SAW atas tanda cinta kita pada dia. Sebab kalau kita cinta, kita kena tahu every single thing about Rasulullah SAW. So jawapannya ialah soalan pada soalan tu, Ruqayyah dan Ummi Kalsum. A very interesting story. Baru nak angguk Aiman je, tadi tak jawab. So nanti tak apa, kita akan buat kuis lah. Get ready lah Kuantan versus Gombak. Kita ada 3. Kuantan versus Gombak versus Sisters. Wow, 3 grup. Kita tengok siapa menang. Jawab malu Kuantan kita. Kalau kalah ni saya report ke Dr. Ahmad ni. Kenapa ni kena buat satu kursus lagi. Sirah pula pada orang Kuantan. Okay, that's all. Let's end with the doa. Can we have a brother to make a doa today? Baik, orang yang baru kita akan tutup kelas setiap kali dengan doa, dan doa tu kena dibaca oleh brothers sebab I believe brother should lead the ummah. Okay, brother should be ke depan. Kalau medan perang tu awak jangan push Hana, kesian Hana, tiba push saya pula ke medan perang. Oh tidak, awak yang kena ke depan dalam masa medan perang, orang lelaki. So then kita akan rotate each one sampailah habis semester. So semua orang kena baca. So siapakah hari ni? And it has to be voluntary. Kalau tak volunteer, kalau tak ada orang baca, maka kita takkan end kelas ni. Silakan Faris.
Bismillahirrahmanirrahim. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi wa baraka wasallam. Alhamdulillahirabbil alamin.
Tak boleh doa panjang sikit ke Imam? Next time next time. Takkan awak semayang, betul awak semayang dengan isteri awak, baca doa panjang tu je, right? Ini semua adalah untuk preparation untuk awak kahwin nanti tu. Baca doa depan ayah mentua, mak mentua, kenalah lebih sikit. UIA kan? Alright, okay, let's end today's class with tasbih kifarah and surat al-Asr. Subhanakallahumma wa bihamdika nashhadu an la ilaha illa anta nastaghfiruka wa natubu ilaik. Bismillahirrahmanirrahim. Wal 'asr. Innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawasaw bil haqq wa tawasaw bis sabr. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam, madam.
Salam.
Saya akan letak semua recording ni kat YouTube saya. Kalau siapa nak tengok balik.